the next thing I'd like to talk about is sufficiency. So to say an estimator is sufficient is to say that there's no additional information that can be obtained about our parameter from looking at our observation x1 through xn that is not already contained in our estimator. So that is to say, theta hat, just colloquially we'll say is a sufficient estimator if no additional information about the desired parameter theta, so it's an estimator, for some theta. If no information about theta can be obtained from the sample xi's, not already obtainable from theta hat. Okay, but this is a pretty vague statement. How do we actually make sense of this? Get a precise definition. So to do that, we need to think for a moment about how are we doing this in the first place? How are we getting information about parameters using our sample? And let me start by saying something which is perhaps overly obvious. So the setup is we have our distribution. Let's say we think of it as a joint distribution of our n observations, depending on some parameter theta. And we imagine, of course, this is built from some f of x theta, a bunch of IID variables, x1 through xn, but all of type f of x. So let's just imagine, what does this distribution look like? Maybe it's this little bump like that for some particular value of theta, let's say theta 1, but maybe for some value theta 2, the distribution is shifted over to the right. And then, the basic flavor of everything is we start observing start getting our measurements, and we see if they tend to be over here, then the parameter is probably theta 1, and if the measurements tend to be over here, our parameter is probably theta 2, if we're trying to decide between them, right? This is the basic plot. Now, of course, what's the deal? If the distribution didn't look very different between theta 1 and theta 2, it would be pretty hard to do this process. So let me just say, if we can obtain information about theta from our observations, f of x theta must depend on theta. So this is a pretty obvious thing. But this gives us a handle on what it means that all the information about theta is contained in theta hat, or that no additional information can be obtained in some other way. So we say that theta hat is a sufficient estimator for theta. So this is the actual definition. When we take the conditional distribution, so if let's call it, okay, so we're giving a little font trouble here, but this is a lowercase theta, this is an uppercase theta, this is a lowercase theta hat, which is not the same as this guy. This is going to be a specific value of this random variable. This is a random variable. This is going to be a value of the random variable, and that's different from the parameter which doesn't have a hat. Okay, just so we have the font clear. Okay, we say that capital theta hat is a sufficient estimator for little theta if for theta hat a value of capital theta hat, the conditional distribution, so this is f of x1 through xn, which also depends on the parameter theta, but given that the observed value for theta hat is equal to little theta hat doesn't actually depend on theta. So in other words, that means that no additional stuff, so given just this information that that we have this conditional measurement, once we have that, there's no other information that this probability distribution, kind of with this fix, can bring to bear about theta. So this is really the statement that says capital theta hat has exhausted, all the information. So we want to say that for every particular for any value of our estimator, the distribution is now independent of the x's, the conditional distribution. Let's actually illustrate this a little bit first with an example. So bear with me, this is going to take just a little bit of doing. But we're going to look at the sample mean as a estimator for the mean for a normal distribution. Okay. So let's look at theta is going to be the mean. We're going to start with some distribution, which of course it depends on these two parameters, the mean and the variance. So this is just the familiar 1/√2 pi sigma squared e to the minus half of x minus mu squared over sigma squared. Okay, so that's one reasonable way to write it. Okay, and okay, so now of course our joint distribution function, since we have n iids, is going to look like f of x1 through xn mu sigma squared. That's I'm just going to multiply a bunch of these together. I'm going to multiply n of them together. So I have this thing at the n. Those are going to add in the exponent. So I'm going to have, let me grab these guys together, 1/2 sigma squared. Then I have a sum of all my xi minus mu squareds. All right. So now I'm going to do a standard kind of trick, this algebraic manipulation, to kind of take this expression and kind of insert the sample mean inside. So just to fix ideas here, so I'm just going to formally say that this is going to be the sum of my variables. So this is kind of the probability distribution function variable that plays the role of the sample mean. And let me rewrite this using this expression. So what do we have? So xi minus mu squared. So I'm going to think of this as xi minus, let's say, x bar. Not squared there. Plus, I want x bar minus mu. Did I do that right? Yeah, I did. Okay, good. Okay, so it's that thing squared. Now, what happens when you actually square that? So this is these sums are all from I equals 1 to n. I'm just getting lazy and not writing them. But okay, what happens when you square that? Let's go ahead and do it. Xi minus x bar squared. You get these two terms, which are kind of the easy ones. Then you get the cross terms. So twice xi minus x bar and x bar minus mu. And now here's the fun part. When you do that sum, this term is actually going to vanish. Let's just see how that works. So let's note that if I look at the sum from I equals 1 to n of 2xi x bar minus mu, this will actually end up being 0. Let's just see. So we're going to go ahead and FOIL that. I mean, the 2 doesn't really matter. Let me just get rid of the 2 for right now. Okay, so go ahead and FOIL that. I got xi x bar. I get a minus x bar squared. I get a minus xi mu. And then I get a plus x bar mu. And I'm going to take that sum. So this gives me an x bar, sum I equals 1 to n xi, minus n x bar squared, minus mu times the sum of the xi's, and then plus the sum of x bar mu. Okay, so let's see. Now the sum of the xi's, well, 1/n of the sum of the xi's is this thing that we call x bar. So this is n times x bar. And then I get n x bar squared. And then I get mu, the sum of the xi's, that's n x bars. And I get plus n mu x bar. Yeah, boom, 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 boom. All these things go cancel, 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 cancel. The whole thing is equal to 0. As we said. Okay, so this whole thing is actually 0. And let's take a look and see what that gave us. So this was all just rewriting the normal distribution, this joint normal distribution. So let me copy this. This is a trick that hopefully you'll be familiar at some point, if it isn't already. So this ended up being equal to 1 over root 2 pi sigma squared to the n. And now I have, I'm going to use this, this little algebraic trick here to rewrite this as that. And so I get e to the minus 1 over 2 sigma squared. And now I have a sum of some xi bars, squareds, plus a sum of some, what did I have? X bar minus mu squared, which is really just, you know, n x bar mu. Okay. And that's what we got. So now, of course, this is an exponential, and so I can break this up, this sum inside the exponential, as a product of the exponentials. So I'm going to rewrite this. Bear with me. We're going to get somewhere. We really will, okay? E to the minus 1 over 2 sigma squared. I have the sum of the xi minus x bar squareds. And then I have an e to the minus 1 over 2 sigma squareds. Now this is actually an n on the top, let's say, and x bar minus mu squared. Okay. So that's what we've gotten. Now let's actually go and see what it means that this estimator, that the estimator sigma hat is x bar is sufficient. So it will be sufficient, but let's see why. What we then want to know is that if we take this distribution, so given by this function that we just wrote down, x1 to xn mu sigma squared, and we look at the conditional distribution. So I'm going to just write this like this for the moment, conditioned on x bar equaling some particular value, little x bar, that we want to say that this thing doesn't depend on my parameter mu. So let's see that that's what's actually going on. So how do we actually, let's kind of recall, how do we actually do this conditional distribution? So you might remember the, just by definition, like this is just a little bit of an aside. Let's say I have some PDF f of xy. Let's just print out a joint distribution with two variables just to remember how this works. And I want to look at the conditional distribution where I'm setting y equals some little value y. I guess I shouldn't have two variables there, but you know. All right. If I want to condition this on y equals y, what is that? How do we actually compute that? Well, what do? We look at, I feel like I should use some other, let me call it like y naught or something, right? Some like value, y naught. Okay. So what do? We actually take our distribution, we plug in y naught. Now, this is, in essence, this is what we really want to do. We want to just plug in y naught. The problem is that this is no longer a PDF. It's almost a PDF. It just doesn't satisfy the one kind of critical condition, which is that the integral is 1. And so we need to normalize this by multiplying it by the correct constant to make the integral 1, which turns out to be this marginal distribution of y naught. Okay, the value of that. And that's just how it's defined. It's just that integral right along the x values. Okay, so back to this example, how do I actually compute this or express this marginal distribution? Well, what I really want to do is I want to somehow plug in x bar. Okay, notice like x bar isn't one of these variables, right? But it kind of is, really. I mean, the point is that, I mean, if x bar is the sum of the xi's, or it's 1 into the sum of the xi's, then that means that I can kind of use either as my functions, x1 through xn, or if I wanted to, I could use x1 through xn minus 1 and x bar, because if I know x bar, and I know the rest of the x's, I can solve for xn, right? Xn is x bar minus 1 nth the sum I equals 1 to n minus 1 of the xi's, right? So I can, if you just need to know n of these variables, 1 through n or x bar, right? Okay, so I can think of this as really depending on these variables. So plugging in a value for x bar is really like plugging in a value for xn or something like that. No, in terms of the other ones, right? It's really plugging in this thing. So I could write this. So if I'm trying to emulate what's kind of here on the top, right? So to do this marginal distribution, I could say I'm looking at f of x1 through xn minus 1, and then for xn, I'm writing x bar minus 1 nth the sum I equals 1 to n minus 1 of xi. Okay. This depends in principle on mu and sigma squared. So this is kind of the plug-in part. And now I need to divide by some appropriate constant in order to make the integral equal to 1. So instead of like explicitly writing that anymore, let's just go ahead and copy and examine what we're really doing here. So here's my distribution. And now the point is, what am I doing? I'm gonna plug in I'm going to plug in something over here for the nth one in terms of the x bar. So I'm going to plug in some values over here. So I get this piece is going to involve the x1 through xn minus 1 and x bar after I resubstitute for xn. And then I'm multiplying by this thing. But now what is this thing? If you look at it, this is actually a constant in terms of the x1 through xn minus 1 and x bar. In terms of the variables I'm dealing with right now, not in terms of x bar. X bar, sorry. X bar is not a value, sorry, that's important. X bar is not varying anymore. I fixed a value x bar. I was more careful up here by calling it like a y naught or something like that instead of just the y again. So I should have done the same thing. But here, let's remember that x bar is not a variable. It's actually a fixed number. It's the constant. It's a value. And so this thing doesn't depend on the parameters of my conditional distribution, which are, in essence, x1 through xn minus 1. Right, this kind of depends on these values because x bar is fixed. That determines the xn. X bar is fixed, so this is a number, this is a number. And what does that mean? that means that really my distribution is this animal. Whoops. My distribution is this animal right here. And this is just some scale factor. And then what am I going to do? I'm going to take this thing and I'm going to normalize it so that this scale factor, is switched up so that the final integral is actually equal to 1. But what does that mean? That means that this scale factor, the new scale factor, when I replace that, isn't going to depend on mu. The only thing in this expression where there's a mu is actually over here. There's no mu over here. So when I rescale this thing to make the integral 1, that doesn't have anything to do with mu. That means this new distribution. So I'm going to then, so this is, so when I actually do x1, xn, let me just write it like this, mu sigma squared conditional, the n-1 condition on x bar equals little x bar, then that's going to be equal to, let me just make it a little bit more clear. I get 1 over 2 sigma squared. I get really these guys just coming from I equals 1 to n-1 of I minus x bar, which is just some number. Now, the last one is going to be, so let me move this thing a little bit down. The nth one is going to look a little different. It's going to be plus, and so the nth one is, what is that? X bar minus the sum I equals 1 to n-1 of the xi's. That's the minus x bar squared. So I've kind of plugged that in there. Okay, I get this expression, and then times some constant to make the integral equal to 1. And so that constant isn't going to depend on mu. There's no mu's going on here, so they're not going to be involved in the integral. And we find that this doesn't depend on mu. And that says that our estimator is sufficient. Okay, this was a little bit complicated, but we're going to extract the essential features from this and get a nice, generally applicable criteria for sufficiency. All right, so now let's describe a necessary and sufficient condition for an estimator to be sufficient. So first, let's kind of lay the foundation a little bit. So again, we have some population. The population is described by a particular distribution, which we're going to write for now as some continuous variable with some probability density function f depending on some theta. I could have written it as f sub theta or something like that, but it's some distribution that depends on some parameter of interest. And so now we also have our indicator, theta hat, and by definition, this is some statistic, which is to say it's some function of our sample. So I'll think of it as, I'll use the same letter, theta hat of x1 through x sub n. But I'm thinking about that from that point of view as some abstract function. I mean, I guess I could have given it some letter, I don't know, like we could have said that it's really described by some, by like theta hat is some, I don't know, function k of x1 through xn for some nice function k. Okay, this is what I mean. All right, so let's see. So then we, so the theorem, which is called the factorization theorem, says that suppose, well, okay, yeah. It says that this theta hat is a sufficient estimator for the parameter theta, if and only if we're given, we can, if and only if we can factor our density function f of x1 xn theta as some function which really just depends on, let's call it theta hat. So theta hat, I'm really just calling my my function. Let's say it's k of x1 through xn. So it's something that just depends on this function of x1 through xn and the parameter theta times some other function which only involves my observables, but the critical thing is my sample. But the critical thing is there's no theta here. It doesn't depend on theta. And so, for some functions g and h, and then of course where we really mean that that theta hat is, I guess I already said it, where theta hat has to be given by this particular function of the x1 through xn. Okay, so if we can factor in this way, then we have a sufficient estimator. Now, this is essentially what we did a moment ago when we wrote our distribution. Let's see, where was where we when we wrote our distribution over here as something which involved our estimator and the theta times something which did not depend on the parameter that we're trying to estimate, the theta, which happens to be mu. So this is what we're saying over here. So something that involves our estimator and the parameter, and something that doesn't involve the parameter. And as we said before, kind of unraveling things with the conditional distribution, we were able to, the conditional density function, we were able to see that our estimator was sufficient. Let me sketch at least kind of the other direction. So the general argument is just the same as the one that we gave. I'm not going to repeat that direction, but let's just say just a bit about, a bit of, we'll look at the opposite direction. So that is to say, suppose we know that we are sufficient. Why can we factor? So if we can factor, then the previous argument kind of explains why it's sufficient. Okay, and just to make things simple, let's actually go to the discrete case where I don't have to worry about some more technical criteria. So we'll assume that our variables, these xi, are actually discrete. So instead of talking about our density function, we're going to then describe it by just our probability function. So we'll talk about little p of x, depending on the parameter theta, which is going to be this just probability that x equals x, subject to this is some probability function that depends on theta. Okay, so that's our scenario. And now, so let's suppose that we have a sufficient estimator. So suppose that theta hat is sufficient, which is to say that the conditional probability that x is equal to x, given that our estimator has some particular value theta hat, is independent of theta. It doesn't depend on theta. So that's what our assumption is. Now, of course, here for this to make sense, for for this to make sense, we really need to specify that really theta hat is this particular function of x. You know, I guess I'm using kind of like vector notation here or something like that, right? Okay. So we have, our joint distribution really, which is our vector of these xi's. Okay. So, right. So for this to make sense, we have these x's have to satisfy this condition over here. Okay. All right. So, but what is this conditional probability? So this conditional probability, excuse me, theta hat equals theta is equal to, well, that's just the probability, excuse me, this is the probability, that x is equal to x divided by, well, I guess, and theta hat equals theta divided by the probability that theta hat equals theta. And now, of course, because theta hat is a function of these x's, then this is actually a superfluous condition, because you know, if x's are equal to x, and you know, by definition, capital theta is a function of the capital X, it's the same k. So so if this first thing is true, then this thing also has to be true. So this is the same as the probability that capital X equals little x divided by the probability that theta hat equals little theta hat. That's a capital theta hat. Okay, whatever. Okay. So what does that tell us? That tells us that the probability that x equals little x is the probability that big X equals little x times, this is of course the usual expression, that this is theta hat times the probability that capital theta hat equals little theta hat. And what do we find? We find that because of our assumption on sufficiency, that this expression right here is independent of theta, which is this expression. These are the same expression. So this thing doesn't depend on theta, and this thing is just some function of our, you know, function of our observed value for our estimator, which doesn't depend on, well, just a function of our estimator. And of course it depends on that theta. And so this is our factorization. So this thing is, what did I call it? G and H. So this thing is our H of the little x's, and this thing is our G of theta hat and theta. And there we go. So and you can do the same process backwards, which we basically already did.